Next up, content from Chapter 9, Polymorphism. Polymorphism literally means having many forms. Let's drill down on that. Polymorphism is one of the defining characteristics of object-oriented programming. And in this chapter, we'll discuss the role of polymorphism and dynamic binding, using inheritance for polymorphism, exploring Java interfaces in much more detail, using interfaces for polymorphism, and obviously, or lastly, polymorphic design. So here we look at the method invocation on this slide, obj.doIt. And at some point in time, this method invocation is bound to the definition of the method. If this binding occurs at compile time, then that line of code would call the same method every time. However, Java defers method binding until runtime, which is called dynamic binding or late binding. As I mentioned at the beginning of this lecture, the term polymorphism literally means having many forms. A polymorphic reference is a variable that is able to refer to different types of objects at different points in time. So the method invoked through a polymorphic reference is able to change from one invocation to the next. In Java, all object reference variables have the potential to be polymorphic. Suppose we create the following reference variable: occupation, job. Obviously, occupation is a class, so this is an object reference variable. Java allows this reference variable to point to an object of the occupation class or to any object of any compatible type. And you can get there easily with inheritance. This compatibility can be established using either an interface or, as previously mentioned, inheritance. And when you implement polymorphic references, you can have very elegant, robust designs. But there's a level of care that needs to be taken in using this very powerful tool. So remember our lecture on inheritance. It's important that you understand those paramount concepts as we're talking about polymorphism. An object reference variable can refer to an object of its class or to an object of any class that is related to it by inheritance. An example would be if the holiday class is the parent of Christmas, then a holiday reference could be used to point to a Christmas object or to a holiday object. Here's an example. So we declare an object reference variable using the holiday class, holiday special, but we use the constructor from Christmas, from the Christmas class. Just a quick review of the terms widening and narrowing conversion. In the prerequisite class and in the beginning of this class as a review, you can cast an integer variable to a float or a double. That's widening, and no data will be lost. You have to be careful in casting a float or a double to an integer because that is a narrowing conversion. Assigning a child object to a parent reference is considered to be a widening conversion, and it can be performed by simple assignment, as we saw in the previous example. Assigning a parent object to a child reference is considered to be a narrowing conversion, and you have to do that with a cast. The good news is the widening conversion is the most useful of the two conversions. When implementing polymorphism via inheritance, it is the type of the object being referenced, not the reference type, that determines which method is invoked. So, for example, if we have the mammal class, which has a method called move, and the horse class overrides it. Now consider the following invocation, pet.move. If pet refers to a mammal, it will invoke the mammal version of move. If it refers to a horse, it will invoke the horse version. So it is the object reference variable's type that specifies which method is invoked. Now let's take a look at an application that pays a set of employees using a polymorphic method. So firm has the main method, and we create a staff list of staff members. And it's an array of objects, and the staff member has child classes, volunteer, employee, executive, or hourly. Executive and hourly are children of employee, and employee is a child of staff member, and volunteer is a child of staff member. So in staff member, there is a polymorphic method named pay. And depending upon the type of object that calls pay, remember that object is in an array called staff list of staff members. If it's a volunteer, the pay is going to be 0. Okay? If it's an employee, the pay will be a double. However, if it's an executive or an hourly staff member, it will invoke the pay in those classes. I've got a fully coded solution with all these classes in a Java package, but I'm not sure if I'm going to do this justice in a video. So I'm going to put all of those in the timeline in Canvas, and you're going to have to download these and get this to run on your own computer. So here we have the Java class that calls main, and we create a new staff named personnel, and then personnel calls payday, and payday, right? Payday is going to call for each staff member, each employee in the staff list. It's going to call pay. But when you look at staff members, where is that? I'm sorry. It's up here. When you create your staff, okay, we're going to have a staff list, and we're going to add a new executive. So it'll be an executive object, Tony, a new employee, Paulie, new employee, Vito, a new hourly
employee, a new volunteer. And so when you go to payday and each of these objects calls pay, the pay method, which is the polymorphic method in this application, it's going to calculate a different pay for each of them. So I'll run it for you, but you really need to download these files. Whoops, I'm sorry. It's firm I should be running. And here you could see Tony was the executive. There's his pay. Paulie was just an employee. Vito was an employee, so you can see they got paid. Michael was an hourly employee. And the last two, Adriana and Benny, don't get paid at all because they're volunteers. This is a very complex application. A lot of inheritance going on, a lot of parent-children classes. And in order for you to see the polymorphic method invoking the methods in the different classes, you really need to run this so you know what to do.
Remember, polymorphism can also be accomplished using an interface. A Java interface is a collection of abstract methods and constants. An abstract method is a method header without a method body. It's similar to a function declaration, as we implemented that concept in the prerequisite course to this course. You can declare an abstract method using the abstract modifier. However, if it's in an interface, all methods in an interface are abstract by default, so you can leave it off. An interface is used to establish a set of methods that a class will implement, and we're going to take a look at that very closely. This slide shows an example of a declared interface in Java. Public interface is a reserved keyword, and then we name it doable. And notice that the methods are just the method header. In other words, there is no body. Public void do this, public int do that, public void do this too, etc., etc. You do need a semicolon following each method header. This is very similar to what we did in C++ in the prerequisite course, in a function declaration. An interface does not get instantiated. In fact, it cannot be instantiated. And methods in an interface all have public visibility by default. So there's a class that formally implements an interface by stating so in the class header. And we're going to take a look at that class header in the next slide. And it provides implementations for each of the abstract methods in the interface. If a class states that it implements an interface, it must define all of the methods in the interface. You can't leave any undefined methods. So here we have an example of a public class can do that implements is a reserved keyword, implements doable, which was the interface we saw, I don't know, 2-3 slides back. Every method listed in doable must have a definition in the class that implements the interface. In addition to implementing all of the abstract methods in the interface, a class that implements the interface can also implement other methods. And in addition to or instead of abstract methods, an interface can contain constants. When a class implements an interface, it gains access to all of the constants that were declared in the interface.
Now let's take a look at a Java.
In a UML diagram, the relationship between a class that implements an interface and the interface is depicted using a dotted arrow. Here we can see secret is implementing the interface encryptable, and we also use two less than signs and two right-hand signs, two less than signs and two greater than signs to encase the term interface to indicate that encryptable is an interface. A single class can be used to implement multiple interfaces, and you simply list the interfaces in the implements clause, or right after the implements clause, and they are separated by commas. The Java API contains many interfaces. The comparable interface contains one abstract method called compareTo, which we use to compare two objects. This was discussed in chapter 4, where we use the compareTo method of the string class, because the string class implements comparable, giving it the ability to put strings in lexicographic order, which is how strings are compared one character at a time using their numerical equivalent in Unicode or ASCII. Any class can implement comparable to provide a mechanism for comparing objects of that class's type. So if obj1.compareTo obj2 is less than 0, obj1 is less than obj2. The value which is returned from compareTo will be negative if obj1 is less than obj2, 0 if they're equal, and positive if obj1 is greater than obj2. When you design a class implementing the comparable interface, it should follow this intent. So there should be a way of comparing objects in that class. To continue the thought of implementing the comparable interface, it is up to the programmer who designs a specific class to determine what makes one object less than, greater than, or equal to another. So, for an example, you may define the compareTo method of an employee class to order employees by maybe name, maybe last name alphabetically, or by employee number, okay? But the implementation of the method can be as straightforward. If it's by employee number, that's pretty straightforward, or as complex as it needs to be to differentiate objects compared so that the result is less than, equal to, or greater than. Back in chapter 4, we discussed the concept of an iterator. An iterator is an object that provides a way of processing a collection of objects one at a time. We create an iterator by implementing the iterator interface, which contains three methods: hasNext, next, and remove. The hasNext method returns a Boolean result if there are items left to process. That can be your Boolean in a for loop or whatever loop you want to use. The next method returns the next object in the iteration, and the remove method removes the object most recently returned by the next method. By implementing the iterator interface, a class
formally establishes that objects of that type are iterators. Therefore, the programmer must decide how to implement the iterator functions. For example, you might use the for each version of the for loop to process the items in the iterator. You could write a class that implements certain methods without formally implementing the interface. An example here would be if we want to implement the method compare to without implementing the interface comparable. However, formally establishing the relationship between a class and an interface using the implement reserve word allows Java to deal with objects in certain ways, which, as you guessed, based upon the topic of this lecture, brings us back to polymorphism. Now let's develop the important relationship or linkage between polymorphism and interfaces. So here we have an interface named speaker that has two abstract methods, speak and announce. This interface name can now be used as the type of a reference variable. So we can create a new speaker reference variable. In this example on this slide, we're naming it current. And that object reference variable can now point to any object of any class that implements speaker. You probably can see where this is going if you've been paying attention to polymorphism and understand the concepts that we've been building here. You can clearly see where this is going. So here we have current invoking the speak method. Remember, current was an object reference variable created from the speaker interface. Any class that implements the speaker interface can use current as an object reference variable to an object of that class. So, and it can also have its own speak method body implementation. So this is the version of speak that the following line invokes depends on the type of object that current is referencing. This is analogous to the technique for polymorphism using inheritance. This is clearly a different way of implementing polymorphism. Now we pull it all together. Now follow me on this because this is really the coup de grace as far as polymorphism via interfaces. This is really how it works, the nuts and bolts. So suppose we have two classes, philosopher and dog, that both implement the speaker interface, and both of them provide different versions of the speak method. So in the following code, the first call to speak invokes one version of the speak method, which is defined in the philosopher class. And so guest.speak after the guest object reference variable created with the speaker interface reference calls speak that is a method defined in philosopher class. Then we reassign the object reference variable guest because dog also implements speaker. And then when we call in the last line of this example, when guest.speak is invoked, the version of speak is defined within the dog class. So we clearly have multiple versions, i.e. polymorphism.
that's the end. I hope this was useful. Obviously, this is a really, really important concept. And if you have any questions, don't hesitate to ask me. And we'll talk about this more, and we'll have activities to bring this all together. Thanks for watching. Take care.